Hi everybody, welcome to another video in discrete math section 5.3 and 5.4. I put these two sections together. It have a lot of common thing. Right. So first we recursively define a function. So a recursive or inductive definition of a function consists of two steps: the basic step and the recursive step. The basic step is specify what happened at the function at 0 or the initial values, and then the recursive step is how do we get from this state to the next stage. Right. And the function is the same way we have the recurrent relation that discussed in section 2.4. Right. Let's look at some example. Suppose f is defined in that way that f of 0 is equal to 3, f of n plus 1 is equal to 2 times f of n plus 3. Right. So in that case, find f of 1, 2, 3, and 4. So we have f of 0 is 3. Now we want f of 1. If we want 1, we're going to let n equal to 0, right? So 0 plus 1 is 1. And then it will be 2 times f of 0 plus 3, right? This is when n equal to 0. And we substitute into here. Alright, so 2 times f of 0 is 3 plus 3. So that is 9. Now we want f of 2. That is when n equal to 1. So put 1 in here. That makes f of 2. Be 2 times f of 1. And f of 1 is equal to 9. So that is 18 and 3, 21. I'll just keep doing that. N equal to 2. So put 2 in here. That gives us f of 3. And 2 times f of 2 plus 3. 2 times 21. Plus 3, that's 42, that's 45, and n equal to 3. 3 plus 1 is 4, 2 times f of 3, plus 3. F of 3 is 45, plus 3 is 93. Right. Now if we use a calculator, we can do this heat math, mode, make sure it is in the sequence mode. So we do this like the recursive or recursion relation, give that in sequence. Right, y equal to, right, we start with f of 0 is equal to 3, right, and f of n, we don't have n plus 1, so we start with f of n equal to 2 times u of n minus 1 plus 3. And then let's go here. So I have 3, 9, 21, 45, and 93. So just like that. Once again, the recursion. We cannot type like n plus 1 and n, so we have to use n and n minus 1. Initial values, we start at 0, and u of that value is equal to 3. So this is just like what we have earlier. Right, next, recursive define this summation. So let's say if ak equal to 0, we just have a of 0, right? So at 0 we have a of 0. And then for k, we can just write a naught and then so we can write one term before that. Okay, Let's try that. Now, all of this can be written as a summation from k equal to 0 to n minus 1. H of k, and then with plus h of n. Sorry, this is n because it goes from 0 to n. Yeah, so that summation is equal to this summation. And so the recursive definition we have equal to n minus 1 plus h of n. And we can write this as s of n. And we say s of 0 is equal to a0. Yeah. So we write that. So this is the recursive definition. S of 0 is a of 0. And then for that, we just do recursively is equal to s of n minus 1 plus h of n. Yeah, so that is the recursive definition. Right, next we have Fibonacci numbers. Fibonacci numbers is start from f of 0 is 0, f of 1 is 1, and then whatever this is, the next number is equal to the two numbers in front of it add together. Of course, we can just use this form. So we have 0 and 1, so f of 2 is equal to f of 2 here, so 2 minus 1, and 2 minus 2. F of 1 plus f of 0, 1 is 1, 0, so it's 1. Yeah. And then we can just keep doing plug in this formula, but here you can just write 0, 1, and 1. Now, 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5. We just add the numbers and then write the next. These two numbers combine the next, these two numbers combine the next, and just keep going like that. So 0, 1, 2, 3, 4, 5, actually just up to this term already. Right, so it's like that. The math here, I'm just going to state the theorem here. Let a and b be positive integers with a greater than or equal to b, then the number of division used by the Euclidean algorithm to find the greatest common divisor is less than or equal to 5 times the number of decimal digits in b. Right. Next, recursion definition for sets and structures. And pretty much we do the same thing. Recursive definition is where do we start with, and then how do we go from this step to the next. That's pretty much what we have here. So sometimes the recursive definition has an exclusive rule which specifies the set contains nothing other than those elements specified by the basic step. Right. And then we have other things. Right, just jump straight into some example. The subset of S. So this, let's say we have the set, we start from 3, and then from there, if there are 2 elements in S, the sum is also in S. So we can start with 3, and then we have 3 plus 3 is 6, 3 plus 6 is 9, 6 plus 6 is 12, or 3 plus 9 is 12, either way. So after all done, S will be the set of 3, 6, 9, 12, 15, pretty much everything that is divisible by 3. Right. So that is the subset of an integer S. Right. Next, the natural numbers, and we start from 0, and then we just keep, if it is start from 0, we just n plus 1. If n is in natural numbers, then n plus 1 is also in natural numbers. So we start with 0, plus 1 we have 1, plus 1 from 1 we have 2, 1 plus 2 we have 3. So it's just like inductive proof by induction, we just prove, go to the next. 1 gives us 2, 2 gives us 3, 3 gives us 4, and therefore we have the whole natural numbers. Right. Next we have the strings. The set sigma star of string over the alphabet. We just have start with an empty string, and we just keep adding the character to it. So we start with lambda, and then we just add 0, 1, 0, 0, 0, 1, and then so on. So in that case we have the binary string. Same thing, we can also define trees. We have a set of root trees, a tree like this, or just the binary trees. Of course, the way we define it is like that. Right. I left give you the note here, you can just read it. Right, next, recursive algorithms. Now this is a little more complicated things, and writing this thing is not an easy thing to write. Sometimes we have to think like a computer. Right, so an algorithm is called recursive. It is solve a problem by reducing it to an instance of the same problem with the smaller input. So meaning that a function will call itself doing smaller things. Right, pretty much that's what the recursive algorithm is. So the algorithm will terminate the instance of the problem must eventually be reduced to something initial, which the solution is known. Right. Some sample problem with the recursive algorithm might be to find the determinant of the matrix, or the classic problem of Tau of Hanoi, those kind of, or called dynamic programming. But pretty much a function calling a function itself. Right. Now here's an example. Give the recursive algorithm to compute n factorial, where n is a non-negative integers. So it's like this. Procedures. So the program name is factorial when input is a non-negative integers. If n is equal to 0, return 1. Now this is obvious, because 0 factorial is 1. Next, if it's not the case, n is equal to n factorial of n minus 1, meaning n factorial is equal to n times n minus 1 factorial. Yeah, of course recursively we define factorial this way, but in the program we can definitely say factorial is equal to n times factorial of smaller number, and this program will recall it, and it just keep going back until it equal to 0, then if it's 1. So we just keep multiplying n by n minus 1, n minus 2 all the way back to 1. So that gives us factorial. Right? So the key of recursive algorithm is a function calling the same function inside it. Right, next, give the recursive algorithm for computed a of n, where a is the non-zero real numbers and n is the non-negative integers. So I'm going to try to do something like this. So we start with the name of the program, and let's say n power, or power. In that case there are two input. A is the base, base is, let's say, non-negative, non-zero real numbers. And n is non-negative integers. Non-negative integers. Right. So if we just keep going out, if n is equal to 0 is 1, so we write pretty much the same thing here. If n is equal to 0, then we'll return the values of 1. Other than that, what will return the values will be a times the power of a n minus 1. So pretty much it's equal to a times the power of n minus 1, and then if it recall this and just keep going, it become n minus 2 and then so on. So just keep multiply by a until you don't multiply anything until 1. Right. So another one is finding the greatest common divisor. We call the function itself, just divide by b and the remainder. Just keep doing that. And this is another algorithm, b to the n mod n. Again, I'm just going to write the program here so you can read that. Right. The binary search. Binary search, this is, we talked about binary search earlier, but this time we have the function that binary search recall the binary search. So the program name is binary search. We'll recall it to different case. So remember, the binary search is we search for the values on a list. So we cut in half. And then after we cut in half, we do the binary search again for the upper half and the lower half. So essentially, one of this is the lower half and one of this is the upper half. And whatever value it is, it just keep finding. If it is on the upper half, good, it will find it. If it's not, it will go to the lower half and then just keep doing that. So that's called the binary search. The next one is the merge sort. The merge sort is when we have the list of numbers, we break it down to trees, just one number on each branch, and then we combine the trees together. Every time we add the number into the tree, we rearrange them in the proper order. Like if you have a and 2, the order will be 2 and a. Add in the 4 will be in the middle. And then 6 and 9, you add in 6 and 9, then you scramble. So every time we expand the tree so that at the end of the tree is a number. And then when we merge them back, we align them so it will be proper order. And then of course when we have two strings like this, when we combine, we try to merge together and find the proper order of things. And of course this is the program of it, the merge sort. In that it's called a sub-program merge, and this is this. So a little bit more complicated. I did mention that it is difficult to require programming in this class because everybody might have a favorite programming language, so I cannot require one certain type. For something simple, we can use a calculator, but other than that, at least we'll go over what the algorithm does. But that's all I want to cover in this section. Thank you for watching. See you in another video in Discrete Math.